Okay, this is gonna be a fun one. So what we're doing today is instead of approximating the area and getting an estimate, we're gonna find the exact area using what's called a Riemann sum. So basically our idea that I kind of hinted towards yesterday is we're gonna let these rectangles get really skinny and let the limit of the number of them approach infinity so that they perfectly match any curves of your function and you can find the exact area. Okay, so same idea as yesterday. If we're going to find the exact area of a region that's bounded by a continuous function, otherwise this isn't going to work, over the interval that starts at A and ends at B, what do we need to think about? Well, we're going to think about still dividing that interval from A to B into n rectangles, and the width of your rectangle is still going to be found by taking your end of your interval minus your start of your interval divided by n. So n is still the number of rectangles, my width is still delta x. We're going to find the area using the endpoints of each rectangle and add them all up. So all this beginning stuff is still the same idea. We still want to think of our area of a single rectangle as our width, delta x, times our height. And this u sub I that we've got going on right here is basically whatever current x value I'm at, depending on what rectangle I am currently finding the area of. So like this is changing. We're going to be like cycling through from one rectangle to the next. And this is whatever x value is being plugged in right now. Okay, we're still going to take all those areas and add them up. We're going to write it with our fancy summation notation this time instead of just one by one, width times height, width times height, width times height. So we're going to do the sum starting with rectangle number 1. So I is basically going to represent what rectangle I'm on currently. So starting with the first rectangle until rectangle n, which is my last rectangle, take my width times my height, add all those things together. So like I said, we are doing an infinite number of rectangles, letting that number of rectangles approach infinity so that we can get the exact area, which means I can't go through and one by one plug in whatever x value I am currently at. So I need an expression that I can use for representing my endpoints for my current rectangle. So if you kind of think about it, basically, let me go to my picture up here. Basically, if I start at, let's put actual numbers in here. Say I start at 2 on my x-axis. And these rectangles are, we'll keep it simple, 1/2 wide. This is 2.5. This would be 3. This would be 3.5. I could write an expression for that by saying, okay, whatever rectangle I'm currently at, I've gone over my width a certain number of times. Like I've added 1/2, 1, 2, 3 times here to get to my right endpoint of 3.5. So to represent my endpoint, I'm basically going to say take my start x value, which in this case that I made up happens to be 2, and add my width to it however many rectangles I've gone over. So my width, delta x, or in this case, 1/2 times I, whatever rectangle I'm currently on, is going to give me an expression that represents the current endpoint of rectangle I. So like starting plus width times number of rectangles. So my expressions for my endpoint are gonna have that same idea and look like this. This is just me being fancy and trying to explain here. So rectangle number 1, my right endpoint would be where I started at plus the width of one rectangle. Rectangle number 2 is where I started at plus the width of 3 rectangles. So in general, I can do my starting endpoint of my interval plus the rectangle number that I'm on times my width. And then we're actually going to calculate that, and that's the big idea. This is the same region that we approximated the area of yesterday. Now we're going to get its true exact area. So these seem super complicated. Take it back to width times height and go from there. So think of your width as delta x, and your height is your y values, whatever you get from plugging in your endpoints. So start with your width. Your width is your interval's length, 2 minus 0, divided by n, because we're using n rectangles this time. So we'll have 2 over n for our width, and then thinking about our height's what we get out whenever we plug in the current x value that we are at for our endpoint of whatever rectangle I'm at. And I can represent that expression by saying take whatever x value I started my interval at and go over or add whatever number of rectangle widths that I need to get to where I'm currently at. So here I started at 0, and then I'm going to add I widths of 2 over n, and that will put me at my current x value for whatever rectangle I'm cycling through on here. Okay, so 2I over n is the x value that I'm going to plug in to get the height of my rectangle. I need to actually think about at some point the fact that I'm doing the limit as the number of rectangles goes to infinity, so let me fix my notation here a little bit and write some limits in. Let's also evaluate f of 2I over n. So if you go up to your function and plug in 2I over n for your current x value, we're going to need to do some algebra, so that's going to be my height of whatever rectangle I'm on. I just went ahead and squared my 2I over n. And then let's multiply that 2 over n in here, distribute it a little bit. I tried copy and paste, but it didn't save me that much work. So if I multiply that 2 over n times my 5 minus I squared over n squared, I'm going to get that. And now it's just back to what we've been doing with your sums. So let's break this up, use a couple of our summation formulas, and take the limit. So if I factor out a 10 over n, and think of that as like 10 over n times 1, and then factor out an 8 over n cubed from my second term, I can use my formulas for adding up 1 n times, and that's just going to be 10 over n times n, minus my 8 over n cubed times my formula for adding up perfect squares, which looks like that. And then simplifying and thinking about my limit, I'm going to have 10 minus, and then really if I'm doing the limit as n approaches infinity, only the highest degree term is going to matter here. So I'll have 16n cubed over 6n cubed, and you'll end up with 22 over 3 units squared, or 7 1/3. Okay, now your book decides it's going to throw in notation for definite integrals. This is really just a notation thing. So instead of writing out that long limit expression, you can write this as what's called a definite integral, which is that long, curvy S-looking thing where you write it with your function that you're finding the area between in the x-axis, f of x there, which still stands for your height, and then dx or delta x is your width of your rectangles, and then the top and bottom along your integral symbol are the starting x value and ending x value for your interval. So those are your lower limits and your upper limits of integration. Really, I just want you to know that's long, squiggly S is called a definite integral, and it means the same thing. Also, a note, if your function is continuous on your interval, then your integral's value will exist and you can find your area, like you've been doing. If not, not so much. Okay, so this wants you to practice your definite integral notation. To write it as a definite integral first, so we're going between the x values of 1 and 2 for our lower and upper bounds on our integral. Our function f of x is 1/2 x plus 3, and then notationally we need that dx or delta x in there. But that doesn't help us calculate it. So I'm going to turn it back into the other notation because we actually want to calculate the area here. Oops, I forgot my n on top of my sum. I'll fix it in a minute. Okay, back to width times height. So my width, delta x, is going to be 4 over n. My height, I'm going to use k instead of I here because I don't like I for my index on my sum. So u sub k, my endpoint is my start value of -3 plus my width times the rectangle that I'm currently at, which I called k here instead of I. So I've got the sum of k going from 1 to n of my width of 4 over n times whatever height I get when I plug in the current endpoint's x value. So let's go ahead and plug in -3 plus 4k over n to f and see what our height looks like. So if you plug that into your function of 1/2 x plus 3, you're going to have 1/2 times -3 plus 4k over n, and then distribute your 1/2. And don't forget that plus 3 that you have also. Add them together, you end up with 2k over n plus 3/2. Okay, so there's our height. We will want to multiply our 4 over n times our height, and then use our summation formulas, simplify, and get an area. So doing our multiplication, you get 8k over n squared plus 12 over 2, which is just 6 over n. We could factor out our constants, which means we'll factor out an 8 over n squared, and be left with the sum from k going from 1 to n of k, and then factor out our 6 over n and think of a 1 as being left there. Summation formulas, you'll have 8 over n squared times n, whoops, not k, times n plus 1 over 2 plus 6 over n times n. Only thing that really matters for your limit is going to be your 8n squared over your 2n squared, so you'll get 4 plus 6 is 10 square units.